So welcome everyone to the morning session of the last day. So this session is for the genesis simulations and data intensive astronomy. So my name is Hein Yoon, based at the University of Sydney and a chair of the session. First speaker is Chris Power from UWA, and he's giving an overview talk of genesis simulation. It is a pre-recorded talk because he has another class. So I deliver his apologies for not being here right now. But he will answer your question on Slack or email. So if you have any, I would encourage you to post them on Slack rather than chatting window, and then he will be able to follow up.
Hi there, my name is Chris Power, and I'm going to give you a brief overview of Genesis activities over the last 12 months or so. I'm doing this on behalf of the Genesis team. So if you're new to Astro 3D, it may help you to find out a little bit about what Genesis is. It's one of the threads within Astro 3D, and our goal is to study galaxy formation and evolution over cosmic time using a combination of numerical simulations, n-body simulations, and hydro simulations, and semi-analytical galaxy formation models. We also work closely with our overseas collaborators in the Eagle and the Lustrous TNG collaborations, and we're pretty active at developing in-house software tools for generating and analyzing theoretical data sets and producing mock observables. We're a pretty big team. There's about 20 or 25 students, fellows, associates, and affiliates. It's led by Darren, Stu, and myself. And we have a few postdocs, Kate, Simon, Yisheng, and Manadeep. A quick update on our large n-body simulations program. We've been running these pretty successfully at NCI Gadi over the last year or so. The kinds of runs we're doing consist of between 30 billion up to about 230 billion particles in total. And the runs that we've been doing are ideal for studies of the EOR, satellite dynamics in the local universe, large-scale structure environment, and it ties in nicely with the various projects. At the moment, we're focused very much on trying to improve the scalability of the codes that we use to generate merger trees, which is how we couple to the semi-analytical galaxy formation models. This is non-trivial because we're having to track tens of billions of halos over time, but it's going to be worth it in the long run. Focusing on some research highlights. Considering first the work that Balu's been doing over at the University of Melbourne, he's been looking at extending the mass resolution of n-body simulations for studying the epoch of reionization. And the basic requirements of simulations for the EOR are that we require large volumes and high mass resolution to resolve the full population of ionizing sources. And so Balu's been working on extending this technique that was developed by Yisheng, one of the previous Astro 3D PhD students, which will allow us to resolve all the atomic cooling dark matter halos down to a redshift of 20. So if we look at this plot on the left-hand side, this is showing how this cooling halo mass, halos that are sufficient to accommodate virial temperatures of about 10 to the 4 Kelvin, how that varies with redshift. So the blue curve corresponds to the evolution of this cooling mass. The green corresponds to the resolution of the Genesis simulation, the high-res box that we have at the moment, with about 80 billion particles. And with this new technique, Balu's been able to track halos out to redshift of 20 with an effective resolution of about a trillion particles, or about 10,000 cube particles. And so this is really exciting because we can start to study this in a lot more detail than we might otherwise have been able to. And it's going to allow us to explore the effects of volume and mass resolution on the predictions for the epoch of reionization and galaxy formation physics. Some additional work that's been done over at Melbourne is by James, another PhD student. He's been looking at modeling reionization in cosmological hydrodynamical simulations. And the requirements for James's work is that he wants to adapt the excursion set reionization model based on 21 centimeter fast into full hydrodynamical simulations, which are too large otherwise to do full radiator transfer. So some examples from James's work are shown on the left and the right. So the left shows 50 megaparsec co-moving box, and it's showing the ionization fraction. And you can see that there are large circles in projection that will be centered on star-forming galaxies. And you can see that there's a very good correspondence with the ionizing UV intensity on the right-hand side. It's the same volume, and you can see that there's a very good correspondence between the regions that are fully ionized and those where there's a very high ionizing UV intensity. So James is currently working on a 2 by 2000 cubes particle run, 100 megaparsec box using the same Blue Tides P-Gadget code base. So this is a nice hydro simulation for studying reionization physics. And the idea is that he can then take this formalism and rerun it on the 5,500 cubed particle box at 258 inverse megaparsecs. That's going to be the new asterisk simulation. Moving on to work that's been undertaken by Ruby. Ruby's currently in the final year of her PhD. Ruby's been looking at gas inflows and outflows for centrals and satellites in the Eagle simulations. And in particular, she's been doing some very nice work recently looking at satellite infall events since redshifts of 0.5 onto groups that are more massive than about 10 to the 13 solar masses, and looking at how the gas properties of these satellites are affected over the orbits that they take. So Ruby's been using the Orb-Weaver algorithm that was developed by Reese Poulton, another one of the Astro 3D students that recently graduated. And so she's been able to look at a statistical sample of satellites, 1,000 satellites altogether. And she's been looking at various properties of these satellites. So if we focus on these plots here, each of the panels is plotting a particular property of the satellite galaxies against the time since infall normalized by the orbital timescale. There are 3 different lines. The main one to focus on is the cyan line that corresponds to the lowest mass satellites. And what's particularly interesting, if you focus on the bottom right-hand corner, which is showing the quenched fraction, what you can see is that the quenched fraction rises very rapidly after the moment of first pericentric passage. So in the case for the lowest mass satellites, it takes longer for the more massive satellites to quench. So it's showing the importance of this pericentric passage and the fairly catastrophic gas loss that happens around about that time for the subsequent evolution of this the properties of these satellites. So this is work that's currently in preparation. And Ruby will be talking a little bit more about this later on this morning. Some new work that's being carried out by a new PhD student, Katie Proctor. She's recently started. Katie's looking at the formation of the intra-Halo lights around galaxies, or this diffuse stellar components in the form of the stellar halo and tidal streams and shells. And Katie's particularly interested in how we can learn interesting things about the assembly histories of galaxies by using the IHL. And what she wants is a physically motivated method to define the IHL that can recover the various features that we expect to see there. So what Katie's been doing is she's been building equilibrium galaxy models and then using machine learning to decompose the systems into the various components, in particular the halo, the bulge, and the disk. So if we look on the right-hand side, this is showing in energy angular momentum space what the different components of a galaxy might look like, one of these equilibrium galaxies. So the key point here is that the orange dots correspond to the IHL. And so she's applied a machine learning algorithm, in this case XGBoost, to this data set and used that to train the algorithm, and then applied it to galaxies where we already know what the answer is, but we can see how well it recovers the various components. And so on the left-hand side, Katie's plotted up what the mass profile the mass, enclosed mass as a function of radius looks like for the intra-Halo light. And if you focus on the green curve, that's based on the algorithm that Katie's devised. And you can see that this probability weighted algorithm actually does a very good job of recovering the true intra-Halo mass distribution, which are given by the grey dots. So this is really cool work. Moving on to some very nice work that's been carried out by Diane Triani, or Pippets, over at Swinburne. She's just recently got her PhD, and she'll be moving to ANU to work with Lisa. Diane's developed this new code called Mentari. It's an SED modeling pipeline for modeling the SEDs from the far UV to the far infrared. It's really cool. You can use a web app, or you can actually download the code from GitHub. But the basic model itself includes stellar emission using SSPs from Kurzweil and Charlot, and taking star formation histories and metallicities from galaxy formation models. It includes dust attenuation, so this two-component model of Charlot and Fall, with separate attenuation effects from dust and stellar birth clouds, as well as diffuse dust in the ISM. It also includes dust re-emission using templates from Dale et al. And Sarvazeda et al. So this is available. You can run it on your particular favored galaxy formation model. But Pipet's been using her own Dusty Sage SAM to do this. And probably the key result from this work is that by varying the attenuation parameters based on self-consistent dust tracking within the SAM, she's been able to match the observed Z=0 luminosity functions simultaneously, as well as the cosmic SED as well. And what's important about this is that this can't be done using a fixed attenuation. And so whereas previous SAMs, which did use fixed attenuation, did this, they failed to get the good match that Pipet's been getting, and they required much more exotic solutions, such as a varying IMF. Some very nice work being done by Darren and Ray Sekel, who's one of the Tau developers. They've developed Viz3D, which is this Tau model galaxy visualization tool. So the idea is that you can have an interactive visualization of a Tau galaxy catalog within your browser, and then you can subselect galaxies based on particular properties and download the subselected galaxy catalog for local use. So here's a screenshot. It looks really, really cool. And there'll be a public release in mid-September along with the new galaxy catalogs. So that was a fairly brief overview of the various activities we've been up to as a team over the last 12 months. In terms of like a general assessment of how we're tracking, well, we're doing a diverse range of projects, and they're being carried out across nodes and between nodes. And we have team members embedded within key projects making valuable collaborative contributions. It's really pleasing to see how well our PhD students and junior postdocs are doing. They're particularly productive. They're working on impactful projects. We have really nice collaborations with the Eagle and the Lustrous TNG teams. They're fruitful. They're working really well, and we have team members contributing to the next generation simulations, such as Eagle XL, and working with the co-developers, for example, Swift. And we're getting there with our own ambitious simulations, and they're now up to scale. Getting them up to scale has been pretty challenging, but they produced some important results, and we have some very strong student theses produced along the way. And I think we can say that we're all looking forward to when all the science data products are complete and we're able to start doing some of the cool new science that we want to do. So that's all for now. I'm happy to take questions on Slack.